All right, good morning, class. This is lesson 18, covering section 4.5 of our textbook. So we're almost done with chapter 4. And these last couple sections of chapter 4, we're looking at 4.5 and 4.6. 4.5, we're going to start wrapping up this idea of dimension. What does it mean to have a dimension for a space? How do we find the dimension of a space? I briefly alluded to the dimension of different subspaces, or the dimension of different spaces based on, the number of vectors that we have that's in span, so on and so forth. In fact, that's the very same definition we're going to use for dimension. So part of today's lecture we've already briefly discussed, but now I'm actually going to go into it in more detail, write this out as a formal definition, look at some examples. But a lot of what we have today has already been alluded to. So really, we're just going to put it down officially in words, and we'll have that done and ready to go. So this video might be a little bit shorter, but we'll just see how much time it takes. But otherwise, let's go ahead and get started. Again, this is lesson 18, section 4.5. So we're talking about dimensions. And we just want to get really into the nitty-gritty detail. What does it mean to find the dimension of a space? So, definition: if a vector space, capital V, is spanned by a finite set. So there are a finite number of vectors that its span can be written as. Then what can we say? Well, this tells us that V is finite dimensional. And as previously discussed, for the sake of this class, we're not going to talk about examples of spaces which are infinite dimensional. That's a more advanced topic. Some weird things happen there. But you could see that in other classes, or in the 4,000, 5,000 level. Abstract linear algebra, you could see infinite dimensional spaces. For the sake of this class, we're not going to go that far. All right. So this tells us whether or not we have a finite dimensional space. How do we actually find the dimension? The dimension of V, which we'll write it as written as DIM, we'll abbreviate here. DIM of V is the dimension of V, is the number of vectors in a basis for V. So we call this the dimension because if you think about like R2, for example, sure, I could, if I wanted to, I could write R2 as the span of 1, 0, 0, 1. We already know these two vectors are enough to go everywhere in R2. But if I add a third vector like 1, 1, well, this is still a true statement, right? R2 still equals this span. The difference now is that this set is no longer linearly independent. So this is finite dimensional because it's spanned by a finite number of vectors, but the dimension of R2 is not 3. Why? Because these vectors are not linearly independent. I don't need all three of these to define R2. Two vectors are enough for R2, an x-axis and a y-axis. And so, but we already know this from the spanning set theorem. If you have a linearly dependent vector, well, you can just drop it and it's the same thing. But now that they're linearly independent, I can't drop it any further. And so the dimension of R2 is 2. But we already knew this, right? What's different now is that we can use this fact to find the dimension of all spaces more generally. which we've already been doing to an extent, at least in some of these lecture videos, but now we can formally do it. All right. So the number of vectors in the basis, remember the basis is linearly independent, and by definition, to be a basis, V equals the span of those vectors, which is exactly what we get for the finite set as defined above. And so this is really going to be the key thing for finding dimension. All right. So we do have some special cases we should think about. What if, for example, V contains only the 0 vector? Okay, so you can imagine if I draw this, that means there's a single point, but I can't go anywhere. There's no other vectors. In other words, if you imagine like R1 or R2 or R3, you have some number of axes that you can travel along. In R2, there's 2 axes. In R3, there's 3 axes. In R1, there's 1 axis. But in this kind of space where I only have this one vector and I can't travel anywhere else, there is no axis. There's no vector I can span on. There's no vector that I can travel along. So this is going to be a 0-dimensional space. So it is possible to have a 0-dimensional space. That's when your space is this trivial example of a vector space where you have only the 0 vector. All right. What else can we say? Well, lastly, we can also say if V is not spanned by a finite set, then V is infinite dimensional. And again, for the sake of this class, we're not really going to go into this in too much detail. But if you really want an example, just to get an idea of what to think of as an infinite dimensional vector space, you can imagine something like R raised to the naturals. Instead of raised to like 1 or 2 or 3 or 4, what if it's raised to the naturals? Well, the natural numbers, they are countably infinite. This has countably infinite many different axes. In fact, a vector in this space looks like a sequence. For x in R to the naturals, x looks like this vector, which goes on forever. It's a column vector with infinitely many entries. So it's actually impossible to write this entire column out the way we've been doing, but we've been working with finite dimensional. When it's infinite dimensional, your vector can actually be thought of as an infinite sequence, right? Now, what's the basis for this kind of space? Well, in this case, the basis, you can still think of the identity basis, but now each column just goes on forever. And then for my second vector, I'll have 1 in the second position. And then I'll have 1 in the third position. But I would have to do this all day long in order to write out all of the vectors in this basis. So I'm going to have a vector with 1 in each entry as I continue. This is an infinite dimensional vector space. Now, this is a little bit weird to think about. Yeah. For one, this isn't something we can really draw because there's infinitely many axes. It's an infinite dimensional space. But it has very important theoretical applications. At any rate, that's all I'm going to say about the infinite dimensional space. If you're more curious, feel free to ask me. We can talk about it. But otherwise, we're not going to worry about that for this class too much. Okay. So now that we have this groundwork, we can start to write out some theorems. Now these theorems, they might have some number in the textbook, but again, you don't have to memorize these numbers. What's really important is that you just remember the idea behind these theorems because it can really help you out with different types of problems. So here we have a theorem. This theorem states if V has a basis, which is B1, B2, Bn. Notice it has n vectors. This is an n-dimensional space. Then any set containing more than n vectors is automatically linearly dependent. Why? Well, think about R2 for a moment. We know R2 is two-dimensional, right? We know the dimension of R2 is 2, and we know the basis for R2 is a basis of 2 vectors. So long as the 2 vectors are linearly independent, that's going to be a basis for R2. What happens if I take more than 2 vectors? Well, at any moment, if I take, for example, 3 vectors, well, remember, what does it mean to be linearly independent or dependent? We're looking to see if there's a pivot in every column, right? Vectors are linearly independent if there's a pivot in every column. But if I'm inside of R2, I can never have more than 2 pivots because I only have 2 rows. So for a two-dimensional space, anytime you have more than 2 vectors, it is automatically linearly dependent. And this is going to be the case for any space. If it is an n-dimensional space, the moment you have more than n vectors, you're automatically linearly dependent. This is true for any vector space, precisely for this kind of reasoning. Okay, what else can we say? Let me make some space here. Well, this one we've kind of just already been using, but we have it written out in words. We can have this theorem. If V has a basis of n vectors, then all bases, so we should clarify this for a moment. A singular basis has an I here. A basis is a singular basis. When I say singular, I mean in terms like English, where you can have a singular noun or a plural noun, like dog is singular, dogs is plural. This is what I mean by singular, just think regular English. Basis, that's a single basis, right? Bases, this is the plural of basis, meaning you have multiple of basis. You have for any basis, or this is saying for all bases, right? Basis is plural for basis. For all bases, I lost my place. For V. Must have n vectors. Again, why? Well, if a vector space already has a basis of n vectors, that means its dimension is n. If its dimension is n, that means you must have at least n linearly independent vectors to span that space. Think about R2. R2 is two-dimensional. you need two axes in order to span that space. You need two linearly independent vectors. Every basis for R2 must have two vectors. Okay, so this theorem we already kind of knew, we just haven't written it out. Now this next one, we're thinking about subspaces. And this one you probably could have already guessed, but let's take a look. Let's say let H be a subspace of some vector space V with finite dimension. So this theorem only applies in the finite dimensional case, which is good because that's all we're using for this class. Let H be a subspace of V with finite dimension. Then the dimension of the subspace is less than or equal to the dimension of the vector space. Why? Well, let's think about this. For some subspace, that subspace is a subset of whatever space you're talking about, right? If I'm thinking about R2, H is a subset of R2. It has to be inside of R2, which means at most, H could be all of R2, in which case they have the same dimension, but H can never be bigger than R2 because to be a subspace means you are a subset. You can never get bigger than the space you're inside of. So the dimension is kind of capped. It has this upper bound of whatever the dimension of the space it's inside of. But it can also be less than the dimension of the space it's inside of, because think about, well, what if H is the span of 1, 0? Right? We've looked at this subspace before. This is the subspace which is just the x-axis and only the x-axis. You can only travel back and forth on the x-axis. This is a one-dimensional subspace of R2 because it only has a basis of one vector. The basis here for H, let me be clear with the language. H is the span, right? Without span, this wasn't a space, right? Just the set of 1, 0 was not a space because it doesn't have the 0 vector, first of all. But now that I put span, now it is a vector space. You have to have span here. Saying H equals the set of 1, 0 is wrong. H equals the span of 1, 0, but its basis is a single vector. No span, just a single vector. So it has one dimension, and it is less than the dimension of R2. So we can see examples where the dimension is smaller than, but it can never get bigger than the space it's inside of because every subspace is a subset. All right. So that's good. And you probably may have already knew that, or at least maybe you had an intuition to think that was true. But we hadn't formally discussed it. Okay, what else can we say? Well, when we're talking about dimension, we can also think about the dimension of the column space, the dimension of the null space, the dimension of the row space. In all of those examples, what is the dimension? Well, just like we have for our definition, the dimension is the number of vectors in its basis, right? Now, what we did previously, I believe it was 4.3, maybe 4.2, when we talked about column space, null space, row space. We talked about how to find their bases, and that was based on finding where the pivots are, how many columns with pivots can we find, how many free variables there are, so on and so forth. And so we have these definitions written out here. So these are definitions. All right. So the rank of an M by N matrix A. Notice M by N, this does not have to be a square matrix, is the dimension of the column space of A. So rank of A equals the dimension of the column space of A. Oops, too many parentheses. All right. The nullity of an m by n matrix A is the dimension of the null space of A. So the nullity of A, now this one we don't have any fancy abbreviation, we just write it all out. The nullity of A equals the dimension of the null space. Now you want to be careful with notation here. Nullity does not equal null, right? Nullity of A does not equal null of A. Why? The null of A is a subspace. It's a vector space. It's a set of vectors. But the nullity of A, this is a dimension. This is a real number. This is telling us how big the space is, right? So while these two things are related, they are not equal to each other. You can't just swap these terms back and forth, right? They're different things. Okay? So next, this does give rise to a very handy-dandy theorem, which we're going to use pretty much for the rest of the class, for the rest of this summer session. And this is called the rank theorem. Rank theorem. All right, what does this say? Basically, it says the rank of A plus the nullity of A equals the number of columns of A. And this is true for any matrix, whether it's square or not. The rank of A plus the nullity of A always equals the number of columns of A. Why? Well, think about how do we find the rank of A? The rank of A is the dimension of the column space. In other words, it's the number of vectors which are in the basis for the column space. Well, think back. How did we find that? Well, we found that based on how many columns were linearly independent. Remember back in 4.3, or maybe it was 4.2, when we're finding the basis for a column space, we check for which columns are linearly independent, and we take those columns. The dependent columns, by the spanning set theorem, we can drop and forget about. So really, this is the same thing as saying, what is the rank? Well, the rank is actually the number of pivot columns, right? But we knew that from previous sections. What about the nullity? What is the nullity? Well, the nullity is based on the number of free variables, right? Because remember, the nullity is referring to finding these x's, right? The null space is the set of x's such that ax equals 0. But when we're trying to solve for these x's, this means solving the augmented matrix, right? But when you're solving this matrix and you have, for example, if A is a 2 by 2, well, then we have two variables. We have two columns, right? A1 and A2 are columns. And when you're solving this out, the number of free variables tells you what your span is going to be, right? If x2 is free, then x1 is going to be some equation It's going to be some constant times x2, right? And maybe there's another constant, but then when we write out the vector x, we're going to have x1 and then x2 is free. But when we pull this apart into parametric vector form, the number of free variables is going to be telling us how many vectors we have here. Oh, there's no d here because it's 0. Right, because it's equal to 0, there's no constant on this side. Right? The number of free variables is telling us how many vectors we're going to have in our span. This is the number of free variables. Well, these two things together is the total number of columns, right? If all of your columns have a pivot, that means there are no free variables. And so you have all your columns, right? That would be all the columns plus 0 is all the columns, right? So this gives a very nice breakdown for how to find the rank, how to find the nullity, but it also gives us a relationship of if I tell you one of these things, you can use this equation to find the other. For example, if I tell you that A is a 3 by 4 with a rank with the rank of A equal to 1, then by the rank theorem, we have that 1 plus the nullity equals 4. Well, just solve for the nullity, and we find out that the nullity is 3. But again, this makes sense because what does this mean? If the rank of A is 1, that means only one column has a pivot, which means all of the other columns have free variables. How many free variables? Well, there's 3 other columns. So 3 columns have free variables. That's your nullity. That's the dimension of your null space. Okay, so we can do an example that uses this. Let's suppose we have the following matrix A, and here A is equal to the matrix -3, 6, -1, 1, -7, 1, -2, 2, 3, -1, and 2, -4, 5, 8, -4. Okay. Now, for the sake of space and time, I'm just going to go ahead and write out the echelon form. So this is the echelon form after reduction. We're going to find we have the matrix 1, -2, 2, 3, -1, 0, 0, 1, 2, -2, and then all zeros. Now, what is the point of this? Or we can see right away, the rank of this matrix is 2. The nullity, well, that's the number of free variables, is 3. And lo and behold, they add up to the total number of columns. Now, what else can we say? We haven't mentioned row space. Well, remember, row space is the span of the rows. But just like for column space, we only need the linearly independent rows. And for row space, we would take the rows from the reduced form. So the row of A is the span of 1, -2, 2, 3, -1, and 0, 0, 1, 2, -2, right? So the dimension of the row space is also equal to 2. In other words, it's also the number of pivots. The dimension of the row space is also equal to the number of pivot columns, which also equals the rank. Okay, so we have this relationship between the dimension of the row space and the rank. And we have this relationship with the rank and nullity for the total number of columns. Now, the very last thing I want to highlight here is, what does this mean for the invertible matrix theorem? Now that we've talked some about dimensions, we can actually add more information to the invertible matrix theorem. So let's now talk about that. How does this give us more information? All right, so this is the extended invertible matrix theorem. Now, first of all, what do we need to be able to use this theorem? A has to be a square matrix. Let A be a square n by n matrix. Then the following are equivalent with everything previously written in the invertible matrix theorem. So you can go back to when we first wrote out the invertible matrix theorem. And as you might recall, there were like 12, 13 things that we wrote out. And all 12, 13 things we wrote, all those statements are equivalent. Those statements are either all true or they are all false. They all imply one another. So if one of them is true, that means all of them are true. If one of them is false, that means all of them are false. Well, now we have some new statements that we can add to those 12, 13 statements we already had. In fact, we're going to add 5 new statements. Okay, well, what statements can we add? Well, remember, previously, for a matrix to be invertible, we said that is equivalent to the matrix being linearly independent. Well, to be linearly independent means there are n pivots, right? Well, if there are n pivots, that means each column has a pivot, right? The column space is all of the columns because all of the columns are linearly independent. So, but more specifically, what can we say? Well, if we think about that as a basis, that is a basis of n vectors. They're linearly independent. And because they are n of them, that means they are also a basis for Rn. So the columns of A form a basis for Rn. Again, why? There are n columns, so we have enough columns. They're linearly independent because that's what it means to be invertible. And because I have n linearly independent vectors, that gives me n unique directions and unique axes that I can travel in, which is all I need for Rn. So the columns of A form a basis for Rn. Furthermore, this means the column space of A is all of Rn because the column space is the span of these basis vectors. And to be a basis means the span of those vectors is all of Rn, right? So the column space is all of Rn. This is also the same thing as saying the transformation is on 2, right? Remember, the column space is the set of the range. It's the output vectors. Well, if the set of your output vectors is the entire space, you are on 2, okay? What else does this tell us? Well, the column space then has a dimension of n. So rank of A, if the rank is n and is 0 by the rank theorem. But then, like we said at the beginning of class, what does it mean when you have a 0-dimensional vector space? Well, that means you have only the 0 vector. And in fact, this makes sense because remember, for A to be invertible, that means its transformation is 1-to-1, right? What does 1-to-1 mean? Recall that means there are never two different x's which get mapped to the same spot, right? For every x, it only goes to one place and no other x can go there. Well, in order to be 1-to-1, that means only one thing can get mapped to 0. So only the 0 vector gets mapped to 0. This null space cannot have any other vectors in here. Otherwise, it would break 1-to-1. So the null space is only the 0 vector. So all 5 of these statements are now equally equivalent with everything we previously stated in the invertible matrix theorem. So now we have like 17, maybe 18 statements, which are all equivalent. But we had this caveat, just as before, these things are only equivalent when we're talking about square matrices. Okay, let's look at today's participation question. So let me share my screen. Share my screen. Here we go. Okay, sharing. So we are looking at participation day 17. And we're going to answer this question based off of the extended invertible matrix theorem that we just wrote out. So what does this say? Suppose A is a square non-invertible. It is not invertible. If it's not invertible, that means all of the statements we have written are now false. The opposite is true. Okay? So what can we say about the nullity? Well, by the invertible matrix theorem, if A was invertible, well, we just wrote that the nullity would be 0. But if it is not invertible, that means the nullity is not 0. Okay, by the invertible matrix theorem. Well, if it's not 0, what does that mean? Recall that nullity is a dimension, right? Now, you can't have a negative dimension. That doesn't really make sense. A dimension of a space is always greater than or equal to 0. So if it can't be 0 by the invertible matrix theorem, that means the nullity is strictly larger than 0. So we can go ahead and answer the question here. This tells us, if it'll load, here we go. This means that the nullity of A is strictly larger than 0. It can't equal 0 by the invertible matrix theorem. Therefore, it must be bigger than 0. And we figured that out just by this one statement and then applying the matrix theorem. All right. So that's it for today's participation question. And that's everything I have planned for today. If you have other questions, please by all means email me. Feel free to let me know. Office hours are available this evening at 6 p.m. Otherwise, that's all for today. Best of luck, and I will see you tomorrow.